So we've talked about planets and our solar system, we've talked about stars, and we've started talking about galaxies and the universe itself. Now we're going to talk about the universe generally. In other words, we're now talking about cosmology, which is the study of the universe itself. So for a long time, people thought that our Milky Way galaxy was actually the extent of the entire universe. And to be fair, the Milky Way is really, really large. It is so large that it takes light over 100,000 years to get from one side of the galaxy to the other. It is really, really big. So, people figured it is so huge, this could be the entire universe. All of these ideas actually got upended in the 1920s by an astronomer named Edwin Hubble. I'm hoping that Hubble sounds familiar to you. Specifically, what he did is he was able to figure out the distance to what was then termed the Andromeda Nebula. The way he did this was by comparing the luminosity of a star, so the luminosity is the total energy output, compared to its brightness. We mentioned this previously when talking about stars. If we know the luminosity and the brightness, then we can figure out distance, because brightness follows an inverse square law. So if you know the brightness and you know the luminosity, you can figure out the distance. From this, Hubble was able to show that the Andromeda Nebula was actually outside of our galaxy, and in fact, at the distance he determined, it had to be as large, if not bigger, than our own galaxy. Well, after starting to figure out that there are other galaxies out there, one of the other things people started to do was to start taking spectra of these galaxies. So the spectrum is where you take the light and you spread it out into the full rainbow. And then as you look at the rainbow, there are different features that you can look at that give all sorts of really good information. From an object spectrum, you can determine the temperature, you can determine what it's made of, and if you can measure the Doppler shift of it, you can figure out if it's moving towards or away. I believe we talked about Doppler shift previously when talking about waves, but as a quick review, if you have two objects that are coming together, okay, so Doppler shift is about relative motion. So you have the source and the observer. If they're coming together, this causes the wavelengths to squeeze together, so the observer measures or hears a shorter wavelength. If two objects are moving away from each other, then the wavelengths stretch out, becoming longer, and so an observer, if this was a sound wave, would hear a lower pitch. Okay, so this is the overall idea of Doppler shift. You may be familiar with it from a race car. Okay, so as the race car zips past, you can hear it as it's coming close and approaching you. It's high-pitched. Then when it passes and is going away, it drops to low pitch. This is Doppler shift. Here is our first question. How will the spectrum of a star moving toward us change? A, the wavelength of light will be stretched, making it redshifted, or B, the wavelength of light will be compressed, making it blue shifted. Go ahead and think about it, and we'll discuss in just a bit. All right, if the object is coming towards us, then everything gets squeezed in, so it's going to be compressed, which is a blue shift. If objects are moving away, then you get a stretching, which is red shift. If you remember way back when talking about light, we mentioned that red has the longest wavelengths for the colors of light, and blue has the shortest. Technically, that's not true. We say blue, it's actually violet. But blue shift still means that it is shorter wavelengths than what it would be normally. So again, the correct answer is B. The wavelength of light will be compressed, making it blue shifted. So after figuring out the distance to these galaxies that we are now discovering, and then comparing the redshift to these galaxies, Hubble noticed a couple of interesting things. First, he found that almost every galaxy is moving away from us. The notable exception is the Andromeda Galaxy, which is actually the closest galaxy to us, and it is blue shifted, meaning it's coming towards us. Current predictions say that the Milky Way and Andromeda are going to collide in about 2.5 to 4 billion years, which is actually going to be a really awesome show here on the Earth. The Earth and the solar system are probably going to be basically unaffected by the crash, but the interstellar medium, the gas and dust between the stars, is going to get compressed, meaning that the sky is going to light up with 100 times more star formation than what we have right now. It's going to be absolutely spectacular in 2.5 to 4 billion years. I'm not planning on making it that long. Anyway, so first we notice that most things are moving away. Again, there are a little bit, especially the closer galaxies aren't exactly moving away, with Andromeda being the notable exception. The other thing that they started noticing is when you compare the redshift to the distance, we find that the larger the distance, the greater the redshift. Okay, so along this bottom axis, we're looking at distance, and up and down, we're looking at how fast it's moving away. And the farther away the galaxy is, the more redshifted it is, meaning the faster it's moving away. So from this, we can get what's known as Hubble's law. The velocity that it's traveling away from us is equal to Hubble's constant, which is the slope of this line, times its distance. So we can see the farther away the galaxy is, the faster it's moving away from us, and therefore the more redshifted it's going to be. Now, because we're starting to deal with the universe on a large scale, we need to make some assumptions. We call these assumptions the cosmological principle. What the cosmological principle states: now that we're dealing with the entire universe as a whole on this largest scale, we need to make some simplifying assumptions. This is what we refer to as the cosmological principle. And what it states is that the universe is the same everywhere. What we see here on the Earth is going to be the same, and no matter where you are in the universe, what happens here is going to happen everywhere. Again, this is the cosmological principle. So going back to this idea that galaxies are moving away from us, one way of interpreting that is that we are the center of everything. If you think about an explosion, stuff explodes and it all moves away from the central point where that explosion happened. So if you trace back the film, then everything has to end up back here, and therefore we're the center of everything. Now, that does not take into account the cosmological principle. If that were true, then we would actually be in a unique and different position than anywhere else in the universe. But we're going to assume that that is not true. If you think back through the history of humanity, how many times have we thought we're the center of the universe, and how many times have we been wrong? So we'll go ahead and assume we are not actually the center of the universe, and the cosmological principle holds. Well, if the cosmological principle holds, then that means that what we see happening here on Earth has to be true everywhere. So from our point of view here, we see all galaxies moving away. So most galaxies moving away. The local ones, not so much, but that's a whole other thing. Anyway, but if we move to some other far point in the galaxy and we look around, we should see most galaxies moving away from there. And if we go to some other point in the universe and look at the galaxies from that point of view, most of those should be moving away, with the ones farther away moving faster. Well, in that case, if all of that is true, that must mean that all galaxies are moving away from all other galaxies. And the only way that all galaxies can move away from all other galaxies is if the entire universe itself is actually expanding. I realize that's kind of a lot to hold on to, so we're going to go ahead and use an analogy. So in pretty much every textbook that I've ever seen, the analogy that they use is a loaf of raisin bread. Now, personally, I don't know why you'd take a perfectly good loaf of bread and then ruin it with raisins. So instead, I'm going to propose we take a loaf of cinnamon bread with chocolate chips in. Okay, so we have our loaf, we've kneaded it up, we've set it out to rise. As the entire loaf rises, the bread itself is growing. Then, as the whole loaf is growing, it's actually pushing the chocolate chips away from each other. And as we look, every chocolate chip is then going to be moving away from all the other chocolate chips, which is exactly what we see happening. Now, in our case, Instead of a loaf of bread, we have the universe, and instead of chocolate chips, we've got galaxies, but it's the same idea. If the entire universe itself is expanding, then the galaxies are getting pushed away from each other because of the expansion of space. Just like the chocolate chips in the bread are being pushed away from each other as the bread is expanding. Hey, this also helps us understand a little bit of the redshift that we're seeing. The redshift that we see from galaxies was originally understood as a Doppler shift. Okay, this is exactly how Hubble thought it was, that because the galaxies are moving away, their light has been redshifted, and it's just Doppler. That is actually not what is going on. Instead, the redshift that we see happening in light is happening because space is expanding. So what's happening is the light is being emitted at one wavelength. Then, as it's traveling through space, going from whatever galaxy to us, the space itself is stretching, and as it stretches, it's stretching out the wavelength of light. So this is what we refer to as cosmological redshift. It is happening because the universe itself is expanding, stretching that light out. All right, here is our second question. Hubble's law has to do with the A, expansion of the universe, B, steady state of the universe, C, contraction of the universe, or D, cosmic background radiation. Go ahead and think about it, and we'll discuss in just a bit. So Hubble's law is all about A, the expansion of the universe. Because the universe is expanding, the light gets redshifted, and more distant galaxies, the light has taken longer to get from there to here, so it's been stretched out even more, which also means the galaxy is moving faster away from us. So it's all about A, the expansion of the universe.